So in the last video, we introduced the idea of the equilibrium constant as what tells us which way a reaction leans at equilibrium, whether it is product favored or reactant favored. In this video, we're going to be discussing how we can actually calculate the equilibrium constant. And that is using what's known as the equilibrium expression. So this is the mathematical expression that we use to describe the product to reactant ratio. So we can write the equilibrium expression from our balanced chemical reaction. Essentially, what we are doing to write an equilibrium expression is we're taking the product concentrations divided by the reactant concentrations, and all of the concentrations are raised to the power of their coefficient. One little note on notation here. We use square brackets around something to indicate concentration or molarity specifically. So square brackets around X would be molarity of X. We use that all the time as kind of a shorthand notation for saying concentration of a particular substance. So in general, our equilibrium expression looks something like concentration of our products divided by the concentration of the reactants. And these are going to be raised to some power that is coming from the coefficients in our balanced reaction. So again, the square brackets mean concentration. So we've got concentration of products raised to the power of their coefficient divided by concentration of reactants raised to the power of their coefficient. So for a sort of generic reaction here, to be a little bit more specific, if we have A and B reacting to form C and D, we use a different type of arrow to indicate that a reaction is reversible. So this is two arrows pointing in opposite directions. So we can use either this or something like this. Means reversible reaction. Note that this is different from this. It is different, let's see if I can do this better, from this, that these are incorrect and mean different things and are not what you want. Two separate arrows pointing in opposite directions, not a single arrow pointing in both. So back to our example here. Our coefficients are the lowercase letters, and my reactants and products are the uppercase letters. If I want to write the equilibrium expression for this reaction, I put my products on top. They'll be multiplied together when there's more than one molecule on the same side. So I will have concentration of C raised to the C power times the concentration of D raised to the D power. And that takes care of the top or the product side. Then reactants go in the denominator, where I will have the concentration of A raised to the A power times the concentration of B raised to the B power. So this would be our equilibrium expression for this like super generic reaction. Another thing to note is that the equilibrium expression only includes aqueous species and gases. So you have to pay attention to your states of matter. If there are any solids or liquids, they're just left out completely. Don't think of them as being zero because they're not zero. Just ignore them. Omit them. If you want to think of them as being one, you can. But anything solid or liquid is just left out, skipped over, ignored. And this is because the concentrations of these things are constant. They cannot be changed. With something that's aqueous, the concentration changes depending upon how much solvent you dissolve it in. With a gas, the concentration changes depending upon how much volume it's allowed to occupy. But if you have 1 liter of water, that liter of water always contains 55.6 moles of water. There is no way around that. You can't get more, you can't get less. The concentration is always the same. So when you have solids and liquids involved in your reaction, those constant concentrations essentially get just absorbed into the equilibrium constant, so we leave them out of the expression because we don't really need to worry about them since they never change. It is the changing concentrations of reactants and products that control the speeds of the forward and reverse reactions, so the only ones we're interested in are the ones that can actually change. So we just ignore liquids and solids for most equilibrium calculations. Use this information to try to write the equilibrium expression for each of the following reactions. So in the first reaction, all of our reactants and products are gases, which means that everything is going to be included in our equilibrium expression. We don't need to ignore anything since there are no liquids and solids. So we want to remember that we are doing products over reactants. So if we start on the product side, we have NH3 and it has a coefficient of 2. That coefficient is going to become the exponent. So our product goes on top is NH3, and that coefficient of 2 over here becomes our exponent of 2 in our equilibrium expression. That is our only product, so that will be our only term in the numerator. We can go on to the reactant side, which will go in the denominator. We have N2 with a coefficient of 1, so its exponent is 1, which we don't need to write in. We have H2 with a coefficient of 3, which becomes an exponent of 3. In the second reaction, we do want to notice that we have a liquid here. So that one we are just going to skip over, like just ignore it. That's all there is to it. So for this one, starting on the product side, Water we're going to ignore because it's a liquid. It has a constant concentration, so it's not going to affect our equilibrium. O2 is a gas, so that will be included. It has a coefficient of 1, exponent of 1. That takes care of our numerator. On the reactant side, we have H2O2 with a coefficient of 2, which will become our exponent of 2. So this guy just got ignored since it's a liquid. And then our last one, we have solid. Solids also get ignored. And then our products are both aqueous. So we have lead, 2+ times OH-, which had a coefficient of 2. So that becomes an exponent of 2. Now, we can also use the equilibrium expression to calculate the value of the equilibrium constant. So the equilibrium constant, K, is just equal to the value of the equilibrium expression for the system at equilibrium. So if we know concentrations of all of our reactants and products at equilibrium, we can actually calculate the value of K. So why don't you take a minute and try to do that? So the first thing we need to do here is write our equilibrium expression for this reaction. So starting on the product side, we have the hydronium ion, H3O+, with a coefficient of 1, times this A- ion with a coefficient of 1, so both of those have exponents of 1. On the reactant side, we have HA, so we'll do the concentration of that in the denominator, and then water is a liquid, so it gets ignored. So calculating the value of K is just going to be taking our concentrations. We're told that at equilibrium, we have these concentrations, and plugging them into our equilibrium expression. So H3O+ was 0.05 molar, A- was the same, and then HA was 0.95 molar, which gets us a value for K of 2.6 times 10 to the negative 3. So we can see that K is fairly small here. K is less than 1. So this is a reactant favored process. Also note that we treat K as unitless. Technically, it does have units that you can work out with all the molarities in your expression what the unit on K would be, but it doesn't actually have any meaning. So we consider the equilibrium constant to be a unitless number.